Hey folks, I've got a quick example for you. It's involving finding the period of a system that's oscillating, and the system is a mass, and it's attached to not one but two springs. All right, and the goal is to find the period of oscillation, T. Okay. Now, if you need a moment, please pause the video and just copy down the sketch with the K1 and K2 and the mass in it. There you go. All right. And then I did write down for a single mass vibrating on a spring, I wrote down the period. So the first tendency for students oftentimes is to say, oh, okay, for K, I'll just add K1 and K2, and then that'll be my answer. And that would be wrong. Okay, so don't do that. All right, so how do we figure this out? Well, the general strategy is the following. We want to get A in terms of X. And there should be a negative out front here, and whatever's in front of that X will be omega squared. And then period will be 2 pi over omega. So that's our goal. Our goal is to get A in terms of X, and then we can get the period, okay? Now, we have to figure out like what X is in this picture. So let's say you take this mass and you pull it to the right some, and now it's over here. Okay. So this is our X. That's how far you've moved the mass. Now, has each spring been expanded a distance X? No. The expansion of this spring K1 plus the expansion of that spring K2 will equal X. Okay, so each spring is going to expand some. The two of them combined will expand a distance X. So just for ease of use, I'll call this expansion of K1, I'll call that Y, and the expansion of K2, I'll call that Z. Okay. So one thing I know is that X will equal Y plus Z, right? So like let's say you move the cart over a foot, maybe Y is 3 inches and Z is 9 inches. The total would be 12. Okay. And that would depend on spring constants, right? The stiffer the spring, the less it'll stretch, and the thinner the spring, the more it'll stretch. Now, we need to get A in there somehow, acceleration. Well, we know that net force equals acceleration, okay? Now, if I draw an FBD of this cart, okay, only spring 2 pulls on it. I'll call that F2. And that's pulling left. So I'm going to make that a negative. So negative F2 equals MA. And again, the only reason I had the negative there is because it's pulling left, the opposite way to displacement. Okay. Now, we also should know, if I look at this spot right there, so spring 2 is pulling to the left or to the right there, that's F2. Spring 1 is pulling left, that's F1. Well, what do I know? If spring 2 is pulling on spring 1 and spring 1 is pulling on spring 2, what do I know about those two forces? Well, they're equal in opposite direction, okay? So it also turns out that spring 1 is pulling left on this cart, the same amount that spring 2 is, okay? Now, it's not touching the cart, okay? But I do know that the magnitude of F2 is equal to the magnitude of F1. Now, the force of a spring is Kx, but in this case, it's going to be a Y or a Z. So the force of, oh, sorry, force 2 equals force 1. Sorry about that. I wrote force 2 equals force 2. Well, that would be true as well, but no, in this case, what's important is force 2 equals force 1. All right, so force 2 is equal to K2 times Z, and that equals K1 times Y. Those forces equal, okay? Now, I need to somehow get X in here, all right? So what I want is I'm going to sub in here for Y, I'm going to put, let's see. I take that back. Okay, so let me write it this way. So X equals Y, if I look at this, Y equals F1 divided by K1, right? So I'll shove that in here. This would be F1 divided by K1 plus Z would be F2 divided by K2. Okay. Now, both of those forces are equal, and they equal negative ma. So what I'm going to do next is I'm going to sub in a negative ma everywhere I see an f. So I got a negative ma over k1 plus a negative ma over k2. All right. And now I pretty much got it. I can now solve for a in terms of x. So what I'll do is I'll factor out the negative a, okay, and I'll rewrite this as m over k1 plus m over k2. That equals x. And if I solve for a, if I get a by itself, I get a negative 1 divided by m over k1 plus m over k2 times x. Now, that's a really cruddy fraction. So what I'm going to do is I'm going to multiply by k1, k2 on the numerator and the denominator. So then I get negative k1, k2 over. If I multiply each of these bottom fractions by k1, k2, the first one becomes an mk2, and the second one becomes an mk1. That's still all times x. And then I'll simplify this one step further. I'll draw the negative out. And in here, I have a k1, k2 over, I can factor the m out there, and we get k2 plus k1 all times x. So that is a in terms of x. So there's your hard part. Now the easy part is figuring out the period. Okay, whatever's in front of the x, so all this is omega squared. So period is equal to 2 pi over omega, which is 2 pi root the reciprocal of that fraction. So you would get m times k2 plus k1 over k1 times k2. And if you want to, take the reciprocal of that, okay, let's see. Oh, wait, I take that back. I lied. Oh, gosh. Sorry about that. So anyway, omega squared is just this. So just write that in. It's square root of that. So k1, k2 divided by m times k2 plus k1. There you go. All right, and so if I want to rewrite this without the complex fraction, I just do the 1 over the, or multiply top and bottom of this fraction by the reciprocal of what's in the square root, and you get the following. You get m times k2 plus k1 over k1 times k2, okay? So that would be the period of oscillation of that mass on those two springs, okay? So it's a little tricky. You have to be able to get A in terms of X. So you got to think about, well, how do I get A in terms of X? And you got to do a little, you got to think about, well, Newton's third law, equal and opposite forces. You got to write each force in terms of how far each spring stretches, and you got to do some substitutions. You have to realize that this stretch plus this stretch is going to equal the total motion of the block. So there's a couple things you got to keep track of, okay? The big picture, though, is make sure you keep the big idea there. You want to get A in terms of X. Whatever ends up in front of the X is omega squared. And then we use T equals 2 pi over omega to find the period, okay? The other problem that you're going to see that's like this is, let's say we have a wall, and now the two springs are parallel to each other, like so, and this thing is bobbing back and forth. Well, it turns out this problem is a lot easier. So let's say you call this K1 and this K2. Okay, when you move the block over, both springs stretch a distance x. So that makes that problem a lot easier. And the force acting on that block would simply be F1 plus F2. Both springs are pulling on and touching, therefore pulling the block to the left. So it turns out if you try that problem, and that is one of the problems I think we assigned to you to find that period of oscillation, it's a lot easier than the one I just showed you. So I hope that hint was helpful, and thank you very much.